It's really a pleasure to be here in a real meeting. But before we start, please mute yourselves. So today I want to tell you about work I'm still doing with Amit Kielen's group. We're making nano coils on tips. I work at the QMR Center. Here, I will also point it here, which is in the physics department. And let us start. So what we're making are tiny coils at the edge of tips. So here you can see a gold-plated pipette. And at the very edge of that pipette, maybe I will use the mouse. No, OK. At the very edge of the pipette, you can see us zooming in until at the very end, what we get is this tiny coil. This is about 2-3 microns in diameter that they fabricate for us at the FIB facilities at the Technion. This one is from the Mika facility, but we also work with Laura at the RBNI. And so here you can see that what we're actually doing is we're taking this gold-plated pipette and just blowing away parts of the gold to get this very tiny coil. Here it is. So the black stuff here is the quartz that is underneath the gold. And this picture is taken in a SEM. So except for the sheer pleasure of making tiny stuff, this is also quite useful. And what Amit is working on in his magnetism group are superconductors. I mean, a lot of his research focuses on superconductors. And in recent years, there's been the discovery of these two-dimensional tiny superconductors, which are actually very tiny flakes. So here we can see niobium diselenide samples from Hadar Steinberg's group in the Hebrew University. And as you can see, this is 20 microns. So if you're lucky, you get a few tens of micron size of sample. And so we want to measure these superconductors, which is quite challenging. It is challenging to put leads on them, to connect things to them. And the idea is that with these nanocoils, we can actually use the coil to measure the parameters of these superconductors in the following way. So Amit has been working on these types of measurements for quite a while now. The idea is the following. We have these long, infinite coils, and you place the sample around the coil. So this is the superconducting sample, this blue thing here. And there's a hole through the sample. You place the coil through the hole. And once you put a current in the coil, you don't get a magnetic field on the sample, but you do get a vector potential A that is inside the sample. And so I really don't see this red dot here. OK. So that vector potential inside the sample generates supercurrents. And if we can measure the magnetic moment from those supercurrents, say via a pickup loop that is connected to a squid, then we know A, because we generate it. It's from the coil, from the current on the coil. And we measure J. This is J. We measure it because we can measure the magnetic moment that this sample generates. So we can get the stiffness, the superconducting stiffness of our sample in a very clean way, without any additional wires, without magnetic fields, without vortices. So this is a very, very clean measurement. So this is the idea of what these coils look like. We have this gray quartz pipette, and we have a wire going through it, and then the coil that's on the outside. So we flow the current through the wire at the center, and then it comes back on this coil and generates this infinite coil generates not the magnetic field, but the vector potential around it. So this is a SEM of our biggest coil so far. It has 20 loops, but we're improving and improving. We just started this project This is maybe our third or fourth such coil that we made. So of course, these coils are not really infinite, and they do have some angle because of the pulling of the pipette, but we can make accurate calculations. We know the exact shape because we take them to SEM, and we can really calculate what the magnetic field is outside, how close it is really to zero. And well, it's hard to see the numbers, but this is less than 1% of the magnetic field at the center of the coil. So it's a very low field, and we can play with the numbers and get fields that are close enough to, well, zero for our purposes. And so now a moment of shameless advertising. These measurements were done at the QMR Center, which I run. And this machine is the MPMS. It's the magnetic property measurement system that has a squid and can measure signals down to less than micro EMU. And we have all kinds of equipment in our center. So you're more than welcome to come and measure with us. And so we'll show it now. The results were measured with this MPMS. So here you can see the results of a tip that we measured. This is the tip. I mean, this is the pulled pipette. The tip is here at the very end. And these are the wires connected to it. And here is the connection. And unfortunately, what we saw in these preliminary results is that there is a very big signal. So this is just the X scale, very big signal coming from the connection of the wires to our pipette. So here, however we choose to connect our wires, we currently see very large signals that are a bit hard to get rid of, and we're currently working on that. But nonetheless, exactly at the location of the tip, you can see a small signal. So there's something definitely there. We are able to measure the magnetic field generated from this coil at the very end of the tip. So you see that if we use plus current, 3 milliampere on our coil, we get a positive response. And if we use minus 3 milliampere, we get a negative response. And if we use 0, it's, well, quite close to flat, I'd say. But it definitely changes sign with the sign of the current. So there's something there. We still can't say how clear and beautiful it is, but we keep improving all the time. And so the future direction, once we switch to a better wire connection, would be to take these tiny flakes and place them around this coil, this nanocoil, and then measure these superconducting samples. And probably we will also need to get a much higher resolution or a much better signal-to-noise ratio. So we started using a DC squid that is dedicated to our purposes, and it is located here. We're currently working on making a lead-shielded place to put our samples inside and measure it very carefully with the squid. And these are the people that made the magic happen, especially the Galit and Lola from the FIB facility, without whom we wouldn't have had these coils. So thank you very much.
Questions? And may the next person come up and attach his computer. Thank you. Yes?
In the measurement you showed, there is asymmetry around the 0.
Right.
What is the
So some of it is probably due to the, how everything is built. We do have to take into account how, the current is flowing. This was just taking the measurement as is. And we didn't take into consideration the exact way that the whole coil was fabricated. Plus, I'm pretty sure that there's a lot of noise coming just from the connection. What I showed was actually soldered, which is a very bad idea. So I'm pretty sure some of the solder joint has some additional signal that also influences what we see at the tip location.
Yes, Yachim.
Nice. So how small can you make the tips themselves?
So
the second thing is that can you concentrate the magnetic field in the edge of the tip?
Right, so we can play with it quite a lot. The smallest tips I know that Eli Zeldov's group make something like 50 nanometers at the edge. Our smallest tips are around maybe a half a micron at the very edge. We usually don't place the coils just at the tip, but we can do it. It's just a question of playing with it in the FIB facility. It's just what spacings we use, what is the pitch of our coil, etc. And we were trying to we have a puller which we're working right now to make play with the angle and just pull tips with different parameters. And many times it just happens that they have a very nice flat area, and then at the tip there's some weirdness. So that's why we didn't use it. But I know other people who do this work and are more experienced than us can make really nice tips that are very flat.
Did you think about the possibility to use these tips to actually generate localized vortices or study the dynamics of these vortices, dragging them?
Right, so specifically we didn't consider vortices, but we are thinking, in the very, very long run. Right now we're just making a coil, that would be a success. To use them for scanning, and then we can not only generate very localized fields, but also pick up very localized fields if you're scanning samples that have magnetic moments or something that you want to measure them not as DC but with some AC characteristics.
Okay, thank you. Let's
Thank
thank
you.
Hannah again.